All right, guys, this is how you do that worksheet on elastic potential energy from Monday, the day I was away. I'll take you through how to do this. You can look this video up, copy down the answers as I go, and hand it in full credit. The symbol for elastic force is simply Fe, force subscript E for elastic. The units on any force is newtons. The symbol for the spring stiffness, the symbol for it is little k, and the units for that spring constant or stiffness is newtons per meter that you stretch that spring or compress that spring. The symbol for any energy, elastic potential energy, even is E with a subscript little e to stand for elastic. Ek was kinetic energy, Eg is gravitational potential energy. The units for elastic potential energy, just like any other energy, is joules, capital J. The equation for spring force is F equals Kx. That's off the PowerPoint that you were given while I was away. Arranging it to solve for K and solve for X, well, we can actually apply a triangle to that because the formula's just got three variables, F, X, and K. So if I want to solve for K, it's simply F divided by X. If I want to solve for X, it's simply F divided by K. The equation for elastic potential energy is E equals 1/2 Kx squared. Solving that for K is a little bit more complicated because I got to move the 2 up and I got to move the X over also, and it becomes something like this. It's going to be 2 times the elastic potential divided by X squared, which is kind of messy looking. Solving for X is even trickier because we're going to have to square root to isolate X. It's going to be 2 times the elastic energy divided by the spring constant and root to get rid of the squared. It's very similar to solving for V when you're looking at kinetic energy. So you've done ones that are that tricky before. The first problem you have to solve says how much force does it take to stretch a spring 2.5 meters? The spring constant is 50 newtons per meter. So force. So don't use the energy formula, use the force formula. F equals Kx, and that's equal 50 newtons per meter times a stretch of 2.5 meters. That's a long way to stretch a weak spring like that, but that's what we're doing here. 50 times 2.5 equals 125. And what's the unit on that? It's a force, so that's simply newtons. Next question says how much energy gets stored in the spring if you've got the same spring constant, same stretch, 50 newtons per meter and 2.5 meters. Well, now it's saying energy, so now you do use the energy formula. Elastic potential equals 1/2 Kx squared. In this case, that's going to be 1/2 times 50 newtons per meter times 2.5 meters, and that is squared. Don't forget to square that x when you're doing energy. So on my calculator, I type in 0.5 times 50 times 2.5, hit my x squared button, hit equals, and I got 156. What are the units? It's an energy, so that is going to be joules. Circle that, and you've done that question. Next question, we got this big picture of a graph. Now, on the PowerPoint, it may have mentioned something about Hooke's law. When you're stretching a spring and it makes a straight line like that, that means that it's obeying Hooke's law. Once you stretch a spring so much that it starts to curve and you start to deform the spring, then it's reached its elastic limit, and then it stops obeying Hooke's law. All the springs that we use in this class, and especially in solving problems, we're going to assume that it follows Hooke's law. The PowerPoint says that the spring constant K is equal to the slope. And in this case, the slope simply rise over run. Because it goes through the origin, I can easily go 500 newtons divided by 0.5 meters. 500 divided by 0.5 is equal to 1,000 newtons per meter. The slope gives you that, newtons divided by meters. So that answers A. A says find the spring constant. Well, we found the spring constant right there. It's 1,000 newtons per meter. Next, it says, how much force does it take to stretch at 0.35 meters? Well, we need that spring constant to do that because it says force. How do we find force with a spring? It's equal to K times X. Now that we have the spring constant, I can put that 1,000 newtons per meter times the stretch that it says, 0.35 meters or 35 centimeters. So I just go 1,000 times 0.35, which is 350 newtons if wanted a force in this case. Last question says, how much energy gets stored in the spring when it gets up to that elastic limit? And there's actually two ways you can do this. I can use the the energy formula for the spring, which is elastic energy equals 1/2 mkx squared. It's probably the easiest way to do it, the way that most people would choose to do it, because that's just going to be 1,000 newtons per meter times how much does it stretch at the elastic limit? 0.5 meters, and that's squared. And that's going to give you an answer. It's going to give you the right answer. Gives me 125 joules of energy. But another way to find it, and another way you have to be aware of, and it speaks of this on the PowerPoint that you went over, is that the energy from the graph is equal to the area. And this graph makes a triangle, so that's going to be base times height divided by 2. The base of it is 0.5 meters. The height of it is 500 newtons, I believe. And then that's got to be over 2. 1/2 times 500 is equal to 250 divided by 2 is 125 joules. You have to be aware of how to get it graphically for possibly thinking and inquiry type questions on your test. You could be given some data, asked to graph it, and it might say part A, find the spring constant, so you got to know that's from the slope. Part B, find the energy stored in the spring, and you have to do that from the area. But if you're just solving a problem, then it's fine just to use both formulas, F equals Kx and E equals 1/2 Kx squared. So hopefully that gets you through that, and that pretty much sums up any problem you'll be asked to do with springs.